Today we are going to solve 0-1 knapsack problem. Let's go through the problem statement first. As you can see on screen, a thief is robbing a store and can carry maximum weight of W into his knapsack. There are n items in the room and each item has a weight and a value associated with it. Considering the constraints of the maximum weight that a knapsack can carry, you have to find and return the maximum value the thief can generate by stealing the items. In simple terms, there are n items in a room. Each item has a weight and a value associated with it. Now, the thief has a knapsack, which is basically just a bag of weight W. His intention is to steal the maximum value which he can generate by picking up items. He is not concerned how many items he is picking up. He just wants to steal away with the maximum value inside his bag. And at the same time, he also has to ensure that he cannot carry items weighing more than W in total. Now we also need to understand why do we call this as 0-1 knapsack. This is because either you can pick the item as a whole and take it in your bag, or you cannot pick it up at all. That means you cannot break an item or take up some part of those items and keep it in your bag. So just imagine you have one item of, let's say, weight 10 kg, right? And you have only 5 kg remaining in your bag. So you just cannot break that item into two and keep one part in your bag. That is not allowed. Here you can either keep it as a whole or you cannot just keep it. Now coming to the sample test case. Let's try to understand this clearly with the help of an example. So if you see, here we have got, first is the number of test cases, then the number of items in the room, then we have the weights of those items, and finally the value of each item. And the very last input, which is 5, is the total weight or basically capacity of the knapsack. So let's imagine I am the thief here and I have a knapsack, a bag of total capacity 5. What are the options I have to pick up from these many items? I can pick an item of 5 kg, and in that case, I won't have any space remaining in my bag, and the total value will be 6, since this item has the value of 6. What else? Now let's say if I pick up the item with weight 4, now I have only 1 kg remaining in my bag. So I can pick the very first item of 1 kg and include it in my bag. In this case, the total value which I'll be having is 8 plus 5, right? Which is 13. Now, in another case, let's say if I pick the item with weight 2. I have 3 kg remaining inside my bag. But do I have any more items of 3 kg? No. I have one item of 1 kg. I can include that, right? Total weight will be 3 and 2 kgs will be remaining empty. So in this case, I will have the value as 4 plus 5, which is 9. Now, I have got these 3 options for this particular example. Now I want to maximize the value. So obviously I'll be choosing the second case and I'll pick the items with weight of 4 and 1. So that the maximum value I can steal is 13. As you can see in the sample output as well. Now let's see how to approach for the solution. So as a thief, I have got 10 items in a room and I have to decide for every ith item whether I should pick it up or I should simply ignore that item, right? I've got 2 options for each of those items. At the same time, I also need to make sure that if the weight of that particular item is more than the remaining capacity in my bag, I cannot keep it inside my bag. So I have to exclude that item. But is that sufficient? No. I have to see the overall combination of items. Basically, I need to generate all the subsets and combinations and see which subset will give me the maximum value. Now, if you hear this thing, subset, generating subset, the very first thing which comes into your mind is recursion. So yes, we'll be using recursion to solve this question. We'll generate the various subsets and we'll try to find the subset with the maximum value. Now, how to solve the recursion problem? What are the conditions we need to write, right? So let's go ahead and see with the help of a diagram. Yeah. So for every item, there are two cases it might fall into. First case is that this item's weight of the ith item is less than or equal to the total weight remaining inside the bag. The second option is the weight of this item, ith item, is greater than the remaining capacity in the bag. Correct? In the second case, since the remaining capacity in the bag is less than the weight of the item, you cannot put that item into the bag. So the only option is to exclude that item from here. Now, if the weight of the ith item is less than the remaining capacity in the bag, I have got two options. I can take it inside my bag, exclude it. So I've got two options. First is the include one, and the second one is the exclude one. Correct? Now we'll see what happens if I include the item inside my bag. If I include this item, the remaining capacity of my bag will become W minus W of ith item. Correct? And since I have made a decision for this particular ith item, or let's say the nth item, how many remaining items are still there? N minus 1, correct? So there are N minus 1 items, and now the weight is W minus weight of item. Now, what happens if I exclude this item? If I exclude this item, then the number of items left from which I can choose is N minus 1 only. The weight remains the same as W, since I have not used any space for this particular item. Same is the case for this exclusion. Since I'm not including that item anyways, the weight will remain as W. And the number of items, remaining items from which I need to decide is N minus 1. So this is basically the recursion diagram. And once you draw this diagram, most of the logic will be clear. In the recursive solution, we have got another thing, which is basically the base condition, correct? Apart from that, we have written the complete logic over here. We have done this, now coming to the base condition. For the base condition, we need to identify the smallest valid input for the changing parameters. So if you see, for every recursive call which we'll be making, what are the parameters which is changing? One is N, it is decreasing, and one is the weight which is decreasing, right? N and W. So as I said, always think of the smallest valid input. So for N, what is the smallest valid input? I can have 0 items in the room, right? That is the smallest thing. And for W, I can have a bag of weight 0. I cannot have a bag of weight minus 1, right? This is where I say that we can find the base condition using smallest valid input. So for N, where there is no items in the room, I cannot pick any item. Eventually, I cannot get any profit, any value out of it. So I'll return as 0. Correct? if the weight of, or basically the capacity of my bag is 0, even then I cannot include any items. And if I cannot include any items, then the profit I'll be making is 0. For both of these conditions, I'll be simply returning as 0. Correct? So since we have understood this recursion diagram, now let's go ahead and code it out. I'll be using C++ for this solution. So we have a function which is knapsack, and we have got two vectors. One is the weight vector and value vector. N is the number of items, and we have got the maximum weight. Now let's do one thing. Let's create a function max. And we'll pass the parameters to it, which is basically the weight, which is value, and max weight. You might be wondering, we already have a function. Why are you even creating this another function? We'll get the answer later in this video. So for the time being, just understand that max profit, and I'm returning the value which is returned by this function straight. Calling function. Now, what exactly do I need to return? I need to return the maximum profit. So that will be int. Function name is max profit. Then I've got a vector of int. I'll pass it through pass by reference. Vector of end of value. I've got the n, which is number of items, and I've got, let's say, w, which is basically the maximum weight of the knapsack. So since this is a recursive function, first of all, we'll have the base condition. As I already explained to you, the base condition is if item is 0 or the bag is 0, we'll simply tell the function to return 0. Actual logic of the code. Now here, for every item, we have got two choices. We'll simply convert the recursion diagram which we have drawn into this piece of code. So remember the diagram? We had the case when the weight of the item, which is in this case, weight of the n minus 1th item is less than or equal to the weight of the knapsack. Correct? If it's less than, then we have got two options. One is to include the item, and the other is to exclude the item. Correct? We'll write the logics here. There is to exclude the item. Correct? Now, once we have answers to this, we need to return the maximum out of those two. Maximum out of the include item and for including the item, if I include this particular nth item into my bag, then at last when I run away after stealing, I'll have this value as well inside my bag. So I'll add this value minus 1th item to my existing answer. One good thing about recursion is that you can just solve for this nth item and tell the function that you somehow calculate the answer to the remaining n minus 1 items. I'll just tell you what I'm doing in this step. For the other steps, you are responsible for calculating the answer. So what we'll do is C function. I'm adding this value, and now it's your responsibility to calculate the maximum profit for the remaining n minus 1 items. So here we'll pass the weight, the value, pass the items, and here since I've included this in my bag, now the capacity of the bag becomes less, which is W minus weight of this particular item. Correct? Since that item has used up some space in the bag. Similarly, for the exclude item, here we are not picking up that item. So I cannot include the value of that item in my final answer. Here I simply need to tell the function, I'm excluding this item. Please tell me what is the maximum profit I'm getting out of the remaining n minus 1. Simply tell the function max profit of weight value n minus 1 items. In this case, I have not chosen the item, so my weight, obviously the weight of the bag still remains as W. And after these two results are achieved, we have two options to return values to the calling function, right? Obviously, I as a thief will choose the value in which is maximum. So I'll return maximum of these two cases, correct? Other cases, if the weight of the nth item is greater than the weight of the bag, in that case, forced to exclude that item, right? So the only option I have is exclude item. Item, the logic will remain the same. That function, please tell me the maximum profit I can get from the remaining n minus 1 items and the weight of W. I'll simply return this exclude item to the calling function. In this condition, you have the. What do you think? Is this solution complete or are we missing something still? Now let's try to run the code and see. So the first test case is correct, and the second and the third test cases, we have got time limit exceeded. So yes, this was the expected behavior. That's why I said that is this complete or still are we missing something? Let's try to understand why we got this time limit exceeded. For every recursive call, since we are making two calls, each of those recursive calls have a state. By state, here I mean they have a particular value depending upon the values of n and w. Since we know that for every recursive call, only the values of n and w is changing, that means here the value will be stored, here some value will be stored, here some value will be stored by calculating the subsequent recursive calls, correct? Now, let's imagine there is a situation where we have calculated this value and all the subsequent recursive calls, and this is for I comma j value, right? Again, in so many recursive calls, there might be a situation where we again come across I comma j. In that case, recursion will again make so many recursive calls over there, similar as this. But do we actually need it? No, because the function has already called for this I comma jth value. Then why is the need to make again? That is why we are getting time limit exceeded. This is basically known as overlapping sub-problems. If you see I comma j, recursive call at I comma j value is one sub-problem which will give you for the answer for I number of items and the weight as j, what is the maximum value the thief can steal. So that is basically sub-problem, a part of the complete problem. And again, at some point, we are getting I comma j. That is overlapping sub-problems. Now, coming to what is the solution for this? One thing is, we can simply store the values for every state. That means for every I comma j, we will store the value in a 2D matrix. That is known as memoization. So let's see if we have already calculated the value of this recursive call by doing all these many recursive calls, then we can simply store this value inside a 2D matrix. Why 2D matrix? because we have only two parameters here which are changing, which is n and w. Correct? That is why we are having a 2D matrix. So this value, let's say whatever the value is, let's say it's 10, we'll store it inside this dp of I comma j. Now the next time the function encounters the same value, instead of making the recursive calls, we'll check whether the dp table has some value stored in it or not. And at the start, we'll initialize all the values as -1, which will indicate that for that particular I and j, we have not made any recursive calls. So recursion, please go ahead and calculate. But if it's not equal to -1, then we'll tell the recursion, stop here only. I'll tell you the value from a table and return. So here we'll avoid so many recursive calls. And that is basically how we can avoid the TLE. Let's make the changes in our code and see what needs to be done. Array, which is basically a 2D matrix of size 10 to the power 3. Why I'm using 10 to the power 3? Because that is the constraint which is given in the question. We have a DP table. Now for every function, every test case, I need to initialize all the values in the DP table with -1. I'll make use of this memset function, which will basically take dp, initialize it to -1, and take the size off. Remember in the start of the video, I had told that you'll understand why I made another function. This is because to make use of this memset. Imagine if I haven't created the other function. For every recursive call, this memset function would initialize all the values as -1. We would have the same problem that we cannot store the values of dp of I comma j of every state. That is why I have made use of this another function. Now let's see what are the changes we need to make inside the max profit function. So as I said, that for every state, right, basically in recursion, every recursion call is the states. In this case, the state is int of n and w, right? So before making a recursive call over here we are calling like line number 7 and line number 8. We'll check if we already have the value stored in the dp table for this state. So dp of w is not equal to -1. That means some value is already there, right? Then simply return the value from the dp table. Dp of n. If it is not there, then we'll ask the function to simply go ahead and calculate the values, right? And apart from calculating, tell the function that you also need to store it in the table once you calculate for a given state. So for this particular state of int n and w, here we are calculating one value, here we are calculating the another value. For both these values, we need to store these into the dp table. So for dp of n w, we need to store this value. Similarly, in this line number 14, which is excluded item. So only this minor change was made to the recursive solution to make it to a dp solution. We are checking it. If the value is not there, then make a call. If the value is there, simply return from the table. And when you are calculating the values, before returning, store it into the dp table. Now let's try to run the code and see the output. So as you can see, all the 3 sample test cases have passed. Let's try to submit and see whether all the hidden test cases are passing or not. So all the 5 out of 5 test cases have passed, and we have solved this 0-1 knapsack problem correctly. So this was all about the solution. Now let's try to understand the time and space complexities of both those solutions, that is the recursive solution and the DP solution. Talking about the recursive solution, we had two options for every item, right? Similarly, for the second item, we had two choices, whether to include it or not include it, and so on for n items, right? So the total number of calls were 2 to the power of n. We'll make two columns, one in time and one in space complexity. So for the recursive one, the time complexity is big O of 2 to the power of n. And for space complexity, we didn't make use of any auxiliary space, but since it was a recursive call, the recursive call stack made use of this space, and hence the space complexity is big O of n. Now coming to the time complexity of the DP solution. Here, for every state I, comma j, right, which is basically for all the values of n and w, we were making recursive calls only when the values were not there in the 2D matrix. So for all the values in the 2D matrix, we made only one recursive calls, which is basically a total of n into w, right? Therefore, the time complexity is big O of n cross w in the case of DP solution. And the space complexity is also big O of n cross w because we made use of a 2D matrix. And that is why it's big O of n cross w of space as well. That's all about time and space complexity for the solution. Hope this